Hi, this lesson is about optimization word problems. So optimization means that we want to maximize or minimize a particular variable. And so most of the problems that we'll be talking about are regarding geometric shapes. So we'll be maximizing or minimizing either dimensions or area or volume. And we use the first or the second derivative tests in order to determine if the values that we have solved for are maximums or minimums. So in general, you're going to want to follow these steps. Sometimes you don't need all of the steps. That depends on the problem. So if applicable, you want to draw an appropriate picture regarding the problem. You want to identify the formulas needed. Usually you'll need two formulas. One is called a constraint formula, and the other will be the formula that you're going to maximize, or that you want to find the maximum or minimum values for. And we find maximums and minimums by taking the first derivative and setting equal to 0. Sometimes you have to substitute. Use one equation in order to substitute into the other equation so that you're only dealing with one unknown variable. Then find the first derivative, set it equal to 0. Those will give you your critical values. And remember, critical values are potential maximums and minimums. And then use one of your derivative tests in order to determine if they represent maximum or minimum values. Okay, so here's our first example. This is regarding two positive numbers. And you're told that the product is 100 and you want to minimize the sum. So the constraint is the restriction that's given in the problem. The product is 100, so x times y equals 100. And you want to minimize the sum, so we're going to let s equal x plus y. Okay, so make sure you identify variables and make sure that the variables between the constraint and the equation that you want to optimize, that you're using consistent variable names. So because the formula that I need to minimize has two variables, I need to eliminate one of them. So I'm going to solve the constraint for y and plug it in to your s equation. So y is equal to 100 over x. So s is equal to x plus 100 over s. Okay, so that's what I have to take the derivative of. So first I'm going to rewrite s as s equals x plus 100 x to the negative 1. So now we take the derivative and set it equal to 0. So that's what you see here. So that's the equation that we have to solve now. And so I'm going to add the 100x to the negative 2 to the right, rewrite it as a fraction. So 1 is equal to 100 over x squared. That's now a proportion that you can cross multiply. So you get x squared equals 100. And when you take the square root of both sides, well, you get x is equal to plus or minus 10. But you can ignore the negative 10 because the original problem said we're looking for a positive answer. All right, so that means that x is equal to 10. And when x is equal to 10, y is also equal to 10 because you plug it in right here. All right, so now we have to prove that x equal to 10 and y equal to 10 provide you with a product of 100 and a minimum sum. So we're going to use the second derivative test to do that. So remember that here's the first derivative. So when I take the second derivative, I get that s double prime is 200 x to the negative 3, which is the same as 200 over x cubed. When you plug in 10, which is the solution we found above, s double prime is a positive number. When your second derivative is positive, it means the graph of this is concave up. And if something is concave up, that means that your critical point is a minimum. So that's exactly what we needed to prove, and we're able to move on. Okay, let's do another. We want to find the dimensions of a rectangle with a perimeter of 100 whose area is as large as possible. So the perimeter is the constraint. You're told that the perimeter is equal to 100. And we want to maximize, because we want an area that's as large as possible, we want to maximize area equal to x times y. So just like in the last problem, the formula that we have to take the derivative of, the a equals xy, has two variables. We need to eliminate one of them. So we solve our constraint for one of the variables. So y is equal to 50 minus x. We plug that in here. So a is equal to x times 50 minus x. All right, so I'm going to distribute in the next line. Makes it easier to take the derivative. So I get a equals 50x minus x squared. And now we're ready to take the derivative. So usually the derivatives in these problems are fairly easy. So my derivative is 50 minus 2x. We set that equal to 0. You get that x is equal to 25. But again, we're looking for dimensions, so you have to find x and y. You find the y by plugging in 25 right here, and so you find that y is also 25, meaning that our rectangle is actually a square. And that's fine. A square is a special type of rectangle. So, as I mentioned before, we need to prove that x and y equal to 25 are dimensions that maximize the area. So I will take the second derivative again. Second derivative of a prime here is negative 2. That means it is always negative, and that means it is concave down, and concave down means that our critical point of 25 is a maximum. Okay, let's move on to another. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So our constraint is the information regarding fencing. So the farmer has this field. He has a fence around 3 sides of the field, no fence where the river is. So that means that my constraint is x plus 2y equals 2,400. Okay, but that's not what we want to maximize. We want to maximize the area. Again, you're told you're looking for the dimensions with the largest area. So similar to the other examples, we need to eliminate one of the variables. So I solve my constraint. And this time I solved for x. It doesn't matter which variable you choose. I'm just going to solve for x. So x is equal to 2,400 minus 2y. I substitute that in here for your area formula. So a is equal to 2,400 minus 2y times y. When you distribute, you get that a is 2,400y minus 2y squared. So now we're ready to take the derivative. So when you take the derivative, you get that a prime is equal to 2,400 minus 4y, and that's what we set equal to 0 to find our critical value. So you end up with y is equal to 600. And because I'm looking again for dimensions, right, we want to find dimensions, the x and y, you plug in the 2,400 right in here, and you find that x is 1,200. All right, so again, we have to prove that the dimensions that we found maximize the area. So again, I will use my second derivative. So a double prime is negative 4, and as I explained before, when you have a second derivative that is negative, that means the graph of the function is concave down, implying that the value that you found, or that we found, is a maximum dimension. Okay, so let's do another. In this one, we're going to use the distance formula. You want to find the point on the parabola y squared equal to 2x that is closest to the point 1, 4. And I put here in parentheses hint, use the distance formula. So when you're trying to find the smallest distance between 2 points, well, that's just a straight line, and that distance is determined by the distance formula. So just to give you a little graphical perspective of this, y squared equal to 2x looks like this. It's a sideways parabola. And the 0.14 is not on the parabola. It's actually above it. So we're actually trying to find what's this value that's probably about here. We want to figure out what is that. That would be, looks like it would be the shortest distance between 1, 4 and the point that we're trying to find. Okay, so y squared equal to 2x, that's our constraint. And the formula that we want to take the derivative of, well, we're going to use the distance formula right here. Okay, so instead of having x and y values, just as I mentioned before, you're going to want to deal with only one variable. So I'm going to take my constraint formula and solve it for x. That's probably a better option than solving for y. If you solve the constraint for y, you're going to end up with a radical, and then you'd have a radical inside of a radical. That could get messy. So I'm going to solve it for x. X is equal to y squared over 2. So right here, when you substitute in, instead of x sub 2 minus x sub 1, it's y squared over 2 minus 1. Where did the 1 come from? From the point. Plus y minus 4. That's the second coordinate. And both of those differences are squared, and you're taking the square root of it. Okay, so now we have a function, and here, this is something you're going to want to remember for future math classes. So if you optimize distance formula, which is what we're doing, that is the same as optimizing the distance formula squared. And why is that helpful? Because if you square the distance formula, the radical goes away. So that's what we're doing right here. I'm going to square d, so d squared. I'm going to call that my function of y because everything is in terms of y. Then you end up with what you see on the right, which is the inside of what was inside the radical above. All right, so in the next line, I'm going to FOIL these binomials. So I'm going to FOIL the y squared over 2 minus 1 squared and the y minus 4 squared. So f of y becomes 1/4 y to the 4th minus y squared plus 1. And then the second binomial becomes y squared minus 8y plus 16. But when you simplify that line, the y squareds cancel, and your new function of y is 1/4 y to the 4th minus 8y plus 17. So this 16 and this 1 combine. So now we're ready to take the derivative. So when you take the derivative, you get f prime of y is y cubed minus 8. And if you set that equal to 0 and solve it, here you get y cubed equals 8. Take the cube root of both sides, gives you a value of y equal to 2. So just like in the other examples, you need to find an x and y value. So you find the x value by plugging it in right here. So when you plug in 2 for y, you get that x is also 2. So now that we found our point, we have to make sure that the point 2, 2 is the point in the graph that will minimize the distance to 1, 4. So remember, this is what f prime looks like. And just to give you a different perspective, instead of using the second derivative, I'm going to use the first derivative test. So if I pick something less than 2 and plug it into f prime, you get a negative result. Like, for example, if you plug in 1 into f prime, that gives you negative 7. So that means the graph is decreasing before 2. If you plug in something greater than 2, like 3, you get a positive result. So when the graph changes from negative to positive, that means that 2, 2 is the point on the graph that minimizes the distance. And by the way, if you look back at our picture here, it looks like pretty much my guess was fairly accurate. So it looks like that XY that I labeled looks like that's just about 2, 2. Okay, let's move on. We're back to a geometric shape, but this time it's three-dimensional. So we have 1,200 centimeters squared of material available to make a box with a square base and an open top. Find the largest possible volume. So the bottom of the box is a square, so therefore our dimensions here are x and x. They're not different, but we don't know anything about the height, so we'll call it a different variable. I'll call it y. So that means that there are 4 panels of either a square at the bottom or rectangles along the sides that make up this box. So we have 1 at the bottom and 4 around the sides that make up the box. Remember, the top is open. It's an open top. So there is no top panel. So my constraint is the sum of all the areas of the panels that make up the box. So that's what you see here. The material is 1,200 centimeters squared. That means that we're adding up all the areas of the bottom part of the box and the 4 sides that make up the tall part of the box. So the bottom of the box is x squared, x times x. Each side panel has an area of xy, but we have 4 of them, so that's why it is x squared plus 4xy equals 1,200. That's our constraint. Okay, think of a constraint as a restriction. We need to maximize, because we don't have to find the largest possible volume. We want to maximize x squared times y. Remember, volume for a rectangular prism is length times width times height, but 2 of our dimensions are the same, so that's why we have x squared y. So first we take the constraint formula and solve for one of the variables. So the better choice here is y. So we solve for y, and you get that y is equal to 300 over x minus 1/4 x when you simplify everything. That y gets substituted into the volume formula right here. So we have, instead of x squared y, we have x squared times 300 over x minus 1/4 x. So before we take the derivative, you want to distribute, again, to avoid product rule. So when you distribute, your volume formula is 300x minus 1/4 x cubed. Okay, so now we take the derivative. The derivative of 300x is 300. The derivative of 1/4 x cubed is 3/4 x squared. We set that equal to 0. And again, you can set it up as a proportion. So add 3/4 x squared to both sides. So we're here. You can get rid of the fraction by multiplying both sides by 4/3. So you get x squared equals 400. And when you take the square root of both sides, you get that x is equal to 20. Again, normally you would say x equals plus or minus 20. It doesn't make sense to have a negative dimension, so x can only be 20. Then you plug it back in here for y, and so you get that y is equal to 10. So we have dimensions of 20 for the base, or the square part of the box, and 10 for the height of the box. All right, but we also need to prove that these dimensions will maximize the volume. So remember, this is v prime. V double prime, by just doing power rule, is negative 3/2 x. When you substitute the value that you solved for x, which is 20, you get that v prime of 20 is equal to negative 3/2 times 20. Well, the answer doesn't matter. All that matters is that it is negative, When it's negative, it's concave down, which means that you have a maximum value. So the dimensions of the box are 20 centimeters and 10 centimeters. All right, here's another kind of fun problem. This is regarding a poster. So the top and bottom margins of a poster are 6 centimeters each, and the side margins are 4 centimeters each. So a margin is like a border. The area of the printed material is 384 centimeters squared. Find the dimensions of the poster with the smallest area. All right, so here's our picture. Here are our margins. I have 6 centimeters above, 6 centimeters below. I have 4 centimeters on each side. And inside, the printed area is 384 centimeters squared. So my constraint is that printed material. So I'm letting the dimensions of the smaller rectangle on the inside be x and y. So my constraint is that x times y is 384. Now I have to minimize the area of the entire poster, which is this and this. Those are the dimensions. Now, let's talk about how to express them. So if I have x units, let's say from here to here, and I have 4 on each side, that means that this whole thing is x plus 8 units. So it's x, then 4, and 4, that becomes 8. Similarly, if I look at my y dimension is this length right here, but then I have 6 more here and 6 more here. So this side is expressed as y plus 12. So those are the dimensions of the poster that I need to minimize, because we're looking for the smallest area possible. So here's our formula to maximize. So area is length times width. So it is x plus 8 times y plus 12. Okay, but we need to solve our constraint for one of the variables. I'm going to solve for y. So you get that y is equal to 384 over x, and we plug that into our area formula. So area is x plus 8 times 384 over x plus 12. So here I have just FOILed out that product. So I get A is equal to 384 plus 12x plus 3072 over x plus 96. And when you combine like terms, the 384 and the 96 becomes 480. And the 3072 over x, well, I've just rewritten that as 3072 x to the negative 1. So now we're ready to take the derivative on both sides. So we do that here. So a prime is 12 minus 3072 x to the negative 2, and we set that equal to 0. So I bring the 3072 over and I rewrite the x to the negative 2 in the denominator. When you cross multiply, you get that x squared equals 3072 over 12. 12 goes into 3072 256 times. That's a perfect square. When you take the square root, that's plus or minus 16. But again, we're dealing with dimensions, so you just want x equal to 16. You substitute back into what y is equal to. Remember, y was 384 over x, so therefore y is 24. So we have our x and our y values, and now we want to prove that those dimensions will allow me to minimize the dimensions of the poster. So here's a prime. A double prime is 6,144 x to the negative 3. When you plug in 16, you get a positive result. And positive means it is concave up. Concave up means that I have a minimum. Okay, but I haven't quite answered the question. Remember, x and y, if I can go back to the picture, x and y are these dimensions. this one right here, for the inside poster, I need to minimize the poster dimensions for the big poster. That has the dimensions of x plus 8, and y plus 12. So as a final step, the work is right here. X plus 8 is equal to 16 plus 8. So one of the dimensions is 24 centimeters. Y plus 12, well, y was 24, so 12 plus 24 gives us 36. So the dimensions of the poster that will minimize the area are 24 by 36. Okay, so now you should try the homework for this section.